Hey everybody, welcome back to another lesson with polynomial functions. This lesson is going to discuss the end behavior along with positive and negative intervals of polynomial functions. So let's get going. All right, so first off, what does end behavior mean? It is described as the y value that the function is approaching on both the far left and far right sides of the graph. So when we're looking at a graph, it's really easy. We'll also discuss how to figure out those values when we look at equations. So the first thing we need to know is the notation for end behavior. And this in light blue that I'm highlighting is the end behavior statement for the left side. And it's read, as x approaches negative infinity, f of x or y approaches, and then we have a blank. That blank will be some value, some number, or positive or negative infinity. The right side end behavior follows a similar format, but it's as x approaches positive infinity on the right, f of x or y approaches, again, some value, a number or positive or negative infinity, just depending on the function. So we can determine that by actually looking at the graph. So in this example, we want to look at the far left-hand side of the function, and that side of the function is increasing and going towards positive infinity. So we would say its end behavior approaches positive infinity. The right side of our graph is going down continually towards negative infinity. So we can say as x approaches negative infinity, remember that's the left, the y values or f of x approaches positive infinity because that side of the function increased upwards towards positive infinity. And when we do the right side, we can say as x approaches infinity, that's the right, then y or f of x approaches, in this case, negative infinity because the right side of our function pointed down continually towards negative infinity. Okay, that's how we do it with a graph. How do we do it with an equation? So our equations can be written in standard form when everything is multiplied all together. F of x equals x to the fifth plus x to the fourth minus 2x cubed is our example. And we're going to look at that leading coefficient and the degree of the function. The degree is the largest exponent, and that term is normally going to be first, and the leading coefficient is whatever number is in front. So this one is an odd degree with a positive leading coefficient. And we'll learn what each of those things mean and how we can get that to help us determine our end behavior. In factored form, we're still going to use that leading coefficient. In this case, it's a -1 for the leading coefficient. And then again, the degree. But in factored form, remember, we have to find the sum of all of the powers of x. And each of these factors just have a single x, so they all have a power of 1. So in this case, we would have a degree of 4, which is even, and a negative leading coefficient. Okay, again, we're going to work through both equations and graphs to help us combine those two bits of information together. So here's our thought process. When we want to determine end behavior of an example, if it's not already graphed, we want to graph it either in the graphing calculator or on Desmos.com. I'm going to use Desmos for my examples. And then our thought process to answer the questions are, look at the degree of the function. So look at that largest exponent and determine if it is even or odd. Okay, so we're going to take care of that first because they each have their own type of end behavior. Then we'll look at the leading coefficient. Is it positive or negative? Okay, we'll determine if the function, once we get it graphed, we'll look to see, does it rise or fall on the left or does it rise or fall on the right? And it could do the same on both sides or it can do opposites. All right, here's our first example. Y equals x cubed. So the degree, there's only one term, so our largest exponent is 3. Okay, so our degree is 3, which is an odd number, so that's an odd degree function because of that exponent. And our leading coefficient, the number multiplied in front of that, is just 1. We don't write it, but it's there, and that is positive. So if we have a positive odd degree function, it's going to do opposites on both sides of the function. So the left side will go down and the right side will go up. Okay, proof, here's our graph. So I went to Desmos.com and I typed in y equals x to the third power, and it gave me this function with points of 0, 0, 1, 1, and then 2 is actually at the point 2, 8. To the left, I have -1, -1, and then the point it's approaching down on the left-hand side is -2, -8. Now, this is a snapshot of the function. It continues on infinitely in both the left and the right directions. Okay, so let's talk about our end behavior. Our end behavior, the left side of the function, right down here, that's falling, that's going down. Okay, the right side of our function, as I follow and trace all the way to the right side, that is increasing or rising. So we can say that the left end behavior, as x approaches negative infinity, f of x approaches, you got it, negative infinity, and that's because the left side of the function goes down. Now on the right-hand side, as x approaches positive infinity, that side of our function goes up, so f of x approaches positive infinity. Great job, guys. We got a few more of these to go through. All right, example 2. We already have our degree up here. Y equals x squared. The degree is 2. That is an even value. Okay, so that's an even degree function. Again, it's a leading coefficient. We don't write the 1, but there is a 1 in the front, and it is positive. So we know this. We've seen these forever and ever and ever. These are parabolas, or that quadratic function. So this is a positive leading coefficient where both the left and the right sides increase. Okay, go to Desmos.com, type it in, boom, here's your graph. We have the vertex at 0, 0, we have a point at 1, 1, and then another one at 2, 4. The right side continues on upwards towards infinity. To the left, we have the point -1, 1 and -2, 4. And again, that left side increases towards positive infinity. So both sides of our function, the left side rises and the right side rises, which means that their end behavior is both going towards positive infinity. Cool. So if it helps you to kind of write these little notes as you're going through, you're more than welcome to do that. On the left, as x approaches negative infinity, f of x rises or goes to positive infinity. It goes up. And on the right, as x approaches infinity, f of x also goes up and approaches positive infinity. Great job. Number 3, y equals -x to the 5th power. My degree is 5. The leading which is an odd number, excuse me, and the leading coefficient is a negative or a -1. Okay, so if we have an odd degree with a negative leading coefficient, the right side has to go down and the left side has to go up. So that's basically what the shape of our graph should look like. It's going to look, boom, there it is, very similar to the cubic that we used in example 1, but this one actually grows a little bit, a lot faster. So we do have the origin 0, 0, we have 1, -1, but the point when we get to the 2 is actually going to be 2, -32. And going towards the left, I'll have the point -1, 1, and then -2, +32. And again, arrows are not there, but they are understood that both the left and the right sides of the function continue. So our left side of our function does continually increase, it rises, and the right side of the function, because that negative leading coefficient, falls. So we can do our end behavior to the left. As x approaches negative infinity to the left, f of x goes up towards positive infinity. F of x approaches infinity. And on the right-hand side of our function, again, looking at the right-hand side of our function, as x approaches infinity, f of x approaches negative infinity. Great job, guys. That one does go down. It approaches negative infinity. All right, we have one more of these to graph on our own. Y equals negative x to the fourth. It does have a degree of 4, which is an even value. So this is an even degree function. The leading coefficient is actually -1. Again, we don't write it, but we see the negative sign. And when we have an even degree function that is negative for a leading coefficient, then the right side and the left side are going to fall down. Now we can do all kinds of humpity bumpity stuff in the middle, but the far left and the far right are going to decrease. When we graph this one in Desmos, again, it's going to look really similar to the quadratic. It's upside down because of the negative coefficient. I have the origin 0, 0, 1, -1, and then at 2, this would be the point 2, -16. On the left-hand side, I have -1, -1, and this other point on the left would be -2, -16. You can find those in the table or looking at the values in Desmos.com. Again, functions continue on forever, even though the arrows aren't there. So let's look at it. What does the left side of the function do? The left side of the function falls towards -infinity. The right side of the function also falls towards -infinity. That's the value it is approaching. I just showed you those other points. They would just be points on the function you could sketch. So the left side into behavior, as x approaches -infinity, f of x approaches -infinity. That side goes down. Okay, and then as x approaches positive infinity, the right side, f of x approaches, again, -infinity because it goes down. So even functions are going to do the same for their end behavior. Odd functions are going to do the opposite. And we're going to put that in a little reference chart. Here we go. Now, this is a little fancy. It's okay. Stick with me. We got this. Not a problem. So n represents the degree of the function, and a will represent the leading coefficient. So if n is an even number, if the degree is 2, 4, or 6, and your a value is greater than 0, meaning it is positive, I'm going to have that quadratic shape, or it can have little humpity bumpies. As long as it's positive, both the left and the right sides of your end behavior approach infinity. Okay, the second set, if your n is even, so again, the degree is 2, 4, or 6, or bigger, and your a value is less than 0, that means it's a negative number, then my function is going to fall down on the right, whether it's single or has a bunch of humpty bumpies in the middle. Okay, so the end behavior for even negatives are going to be -infinity, and even degree positives are going to be positive infinity. Huh, that's kind of a way to remember. Look at that leading coefficient and degree. Okay, the odd degree functions. So if the degree is odd, whether it's 3, 5, or 7, and again, that a value is bigger than 0, so it's positive, remember our odd functions do that opposite on each side. So one side, the right, will go up, and the left side will go down. So right side to infinity, left side to -infinity. And again, you can have multiple curves and humpity bumps in between, as long as the left goes down and the right goes up. All right, last one. When the n value, when your degree is odd, again, 3, 5, or 7, and the a value is less than 0, so it's a negative leading coefficient. That means it's going to flip from the previous example. It'll be its reciprocal. So the left side will be face up, the right side will be face down. So left approaches infinity, right approaches -infinity. And again, doesn't matter how many humpity bumpity things happen in between, left side up, right side down. All right, that's end behavior, and that takes us just at the 15-minute mark. We've got a teeny bit more to do, so we're just going to scooch it on and continue on. It won't take long. Just stick with me. All right, our next part of this lesson is positive and negative intervals. Guys, this is super easy. I just want to know, where is the function above the x-axis and below the x-axis? Above is positive, below is negative. Okay, now there's a couple stipulations. We are going to use the x-intercepts to break up the domain, but we're not going to actually write them in the most precise manner, because an x-intercept is on the x-axis, so it's not included in the above section or the below. Now, to keep things simple, technically it's really wrong, but to keep things simple for us, we're just going to go ahead and go to those x-intercepts and use them and not split it up, okay? If you want to know how that truly works, so that because you need it to be perfect, by all means, come ask us. We can show you exactly how it goes. All right, here's our first example. We are using our graphed function, and we just need to figure out where's the function above the x-axis and below the x-axis. So our positive intervals are going to be highlighted in blue. So from those two x values, looks like that's from -1 to +3. This section is of the graph is where my function is above the x-axis from -1 to 3. Okay, now again, those are x-intercepts. We're just using them to help us get that positive interval. All right, the negative intervals have to be below. So I have one that's on the left that's actually coming from -infinity and stopping at the -1. And then I have another one on the left, or excuse me, on the right, which starts at x equaling 3 and goes out towards positive infinity. So we have two different negative intervals, -infinity to -1 and 3 to positive infinity. We should have a union symbol between those because there's more than one of them. Okay, sections below the x-axis are negative, sections above are positive. Good job, we got a couple more of these. All right, next example, highlight that positive interval. So find where your graph starts to go above the x-axis. It starts at that -2 for x and stops at the 1. So that entire section of our graph, this whole area, is above or a positive section, -2 to 1. All right, the negative intervals occur on the left-hand side from, that looks like that's coming from -infinity to -2. Okay, and then the next one that we have on the other side that's below the x-axis occurs at +1 and continues out to positive infinity. Again, got two negative sections, two parts of the graph that are under the x-axis. So -infinity, -2, union 1 to infinity. All right, two more. We're almost done, gang. Here we go. Positive intervals. I only see one section of this graph. You guys see that? Yep. So it's only this little bitty section over here, but that is going from -infinity to x equaling -2 for my positive interval. So -infinity, -2. Now, we can split up, and technically we should split up this negative interval where it's underneath. I'm going to show you what it looks like all together. Everything from -2 all the way out to positive infinity, keep going and going and going. That's all underneath the x-axis, so that's all negative. So that's what we can write, okay? Now, you could also write -2 to +2 where the other x-intercept is. And then we could pick up again and start at 2 and go out to positive infinity. And we would put a union in between. Technically, what we're supposed to do is then put a bracket of a 2 in there, but that gets a little confusing because 2 is the x-intercept. But again, we can use -2 to infinity. That shows you understand which part is underneath the x-axis. Okay, I think that's it for this lesson. Thanks for hanging out, and we will help you guys come in and ask us any questions. Have a great one, gang.